Hi, myself Khadeeja MJ from S7EB. I'm here to present my seminar on the topic molecularly imprinted polymer-based electrochemical biosensor to creatine detection in renal failure under the guidance of Ms. Winnie and Thomas, Assistant Professor of Department of EB. So these are my contents. Moving on to abstract. Renal failure disease is ranked one of the most prevalent disease with severe morbidity and mortality. Hence, it is important to monitor creatine for timely diagnosis of kidney-related illness and renal failure. So there are a lot of conventional methods for creatine detection, which offers high sensitivity and selectivity. They are accompanied by drawbacks such as long analysis time, the need for sample retreatment, expensive instruments, and skilled personnel. So here the arrival of the biosensor, which provides a highly sensitive, quick, cost-effective, durable solution with excellent detection limits, easy miniaturization, and low sample requirements. But still, the clinical application challenges remain existing there. So on that case, developing MIPs, that is molecular imprinted polymers, along with electrochemical biosensor is essential due to their ease of preparation, storage stability, low cost, reusability, resistance to harsh conditions. So next is reactants, the second most extensively studied biomolecule in clinical research. Electrochemical biosensors is the most classical form of creatine biosensor invented after JAF method. So what is JAF method? JAF method is an electrochemical. JAF method is a colorimetric method. What happening here is the creatine react with picric acid to form orange red complex. We can observe that at the range of 490 to 520 nanometer, and the formation of the orange red complex, which is directly proportional to the concentration of the creatine. So this JAF method have a lot of limitations. So from that, the electrochemical biosensor came into effect. Electrochemical biosensors are most convertible, sensitive, simple, and can be fabricated in miniaturized fashion. Various modifications have been done to achieve the lowest detection limit, high sensitivity by incorporating lot of biocompatible sensitive polymers, nanomaterials, etc. So in my seminar, I'm focusing of the advanced, that is molecular imprinted polymer-based electrochemical biosensor, which offers very low limit of detection and high sensitivity and very low detection time, showing the potential to be deployed in resource-limited setting for the early diagnosis of related issues. So next is the literature surveys that I've gone through. So the first paper, that is electrochemical creatine biosensor for point of care diagnosis of the renal malfunction and chronic kidney disorders. So from this paper, I have taken in-depth analysis of the electrochemical creatine biosensors, highlighting both enzymatic and non-enzymatic approaches. And that paper, they have discussed the limitations and challenges of these sensors also. So the second paper is a recent advance in molecular imprinted polymer-based electrochemical sensor. In that paper, the development and application of the molecular imprinted polymer is discussing, and their advantages such as high selectivity, stability, cost effectiveness. These all things are discussed in that paper. And in the third paper, that is a molecular imprinted polymer, a closer look on the control polymer used to determine the imprinting effects. That is, they are discussing the success of the imprinting factor and that imprinting factor calculation measures, etc. So in fourth paper, that is a method for detection of the creatine, and they're introducing a point of care sensing platform for simultaneous detection of the creatine using a graphene oxide polydopamine molecular imprinted polymer. And this platform utilizes a multi-channel electrochemical readout system with differential pulse voltammetry. And next is the objective. These are the main 5 objectives that I've gone through in my seminar. The first one is to evaluate the limitation of the conventional electrochemical biosensor using enzymatic method for creatine detection and renal failure. So in conventional electrochemical biosensor, one of the main limitation is related to the storage stability of the enzyme. So in conventionally, the electrochemical biosensors are used with the enzymatic, so that storage of that enzymatic is one of the main challenge that they're facing. So that we are introducing molecular imprinted polymers, which is enzymeless reaction taking place there, which offers improved biosensor selectivity and sensitivity. And third objective that are focused is the imprinting factor success for ensuring the MIP metric selective recognition of the targets analyzed. And the fourth one is to introduce a point of care platform for detecting creatine renal failure using MIPs. And finally, to compare the performance of the MIP based biosensor with conventional electrochemical biosensor. So next is the what is creatinine? Actually, creatinine is formed from creatine. This creatinine is produced in the kidneys, livers, pancreas, and then transported to the tissues where is converted into creatine. So actually, creatine is a byproduct of muscle metabolism that enters the bloodstream and can be filtered by kidneys and excreted through urine. So the creatine concentration through determining or detecting the creatine concentration, we get a conclusion that whether any situation or whether any kidney related issues is happening in that human. So next is the concentration of the creatine in each, that is the creatine is not only present in urine as well as it present in urine, serum, saliva, sweat, tears, etc. So the healthy range and harmful range of creatine is explained in this table in men as well as women case also. So in severe cases, creatine level above 500 micromolar indicate abnormal kidney function, which is lead to dialysis or transplantation of the kidney, and were persistently high levels linked to increased mortality. And next, we are moving on to conventional electrochemical biosensors. So, what is biosensor? Biosensor is actually integrated receptor transducer devices. So, what is in receptor is a biological recognition element, which is the thing that recognize the analyte and convert it into readable form by the transducer devices. So the figure is a schematic illustration of the working principle of the electrochemical biosensor. From that figure, it's clear when applying voltage, that is, we are applying this analyte or analyte into that, the biological recognition element binds with it or converted into a product form with the help of an enzyme. Detecting what is the concentration or corresponding concentration can be determined through the transducer device. And next is the electrochemical biosensor is classified into basically four, that is potentiometric, amperometric, contactometric, and impedometric. In potentiometric, we are measuring potential difference, and amperometric is the current, contactometric is the electrical activity of the ions, and impedometric is the resistance. So in potentiometric biosensor, measure the potential difference between working electrode and reference electrode in electrochemical cell. With the working electrode potential varying based on analyte concentration. So in that working electrode, we are placing that our analyte. So the analyte concentration is proportional to the, finally we get a potential difference between this working electrode and reference electrode. We get a conclusion that what's the concentration of the analyte in that particular electrode. So this potentiometric creatine sensor with ammonium sensitive electrode, the equation is given, the creatine plus H2 in the presence of enzyme to form NH4 plus. This NH4 plus concentration, which is proportional to the concentration of the creatine. So 3-enzyme system have also been employed in potentiometric creatine detection. The potentiometric biosensor have a lot of limitations, such as the operational storage stability of the enzymatic receptors as main problem hampering their use in practical application. That is a maximum storage stability that is greater than 6 months at 4 degrees Celsius and operational stability of approximately 90 days with 37% loss in sensitivity. And that I've already mentioned that 3-enzyme system also incorporated can be incorporated in potentiometric biosensor, but by increasing the layers, the immobilized enzymes result in significant loss of its sensitivity. So indifference from endogenous NH4 plus, that is that I've already told that NH4 plus concentration is directly proportional to the concentration of the analyte. So interference is coming along with an NH4 plus, which affect the creatine detection creatine detection is one of the limitation. And next one is the thin layer potentiometer, which is the advanced version of the potentiometric biosensor. Here we are incorporating anion exchange membrane. So this membrane will not allow the cationic species which comes along with the creatine. So this is the feature of this anionic exchange membrane. Only it allows the creatine and it goes to the enzyme and react with them to form the NH4 plus by NH4 sensing membrane. So this Thin layer potentiometric is also have a limitation. That is, the method have a slow response time. That's approximately 15 to 16 minutes. That's one of the main limitation of this method. So moving on to amperometric biosensor. Like in electrochemical reaction, the oxidation and reduction of the chemical species result in the electron flow, which is measured by amperometry. So in the setup, we are using working electrode, reference electrode, as well as a counter electrode. So this is the reaction, and what is happening in the creatine reduction? Creatine react with H2O to form creatine. This creatine again react with H2O to form sarcosin in the presence of enzymes to form sarcosin and urea. So finally, we are getting H2O2, that is hydrogen peroxide. This is a schematic representation of generation of the amperometric biosensor. That is, they are representing the first generation, second generation, and third generation of amperometric biosensor. So this amperometric biosensor has also limitation that is often critical because it greatly influences the operational stability and response of the device. Nonetheless, enzyme of unmatched selectivity towards creatine. And next, moving on to the advanced version of amperometric biosensor based on nanoparticle of enzymes. So here we are incorporating the nanoparticles of the enzymes for enhancing the sensor performance. But it also has some limitation, that is the biosensors enzyme nanoparticle lose 10% of their initial activity after 240 days of regular use. So even when it is stored in 4 degrees Celsius also, it loses its activity, or it loses its ability to active. So finally, because of all these limitations, we are introducing a new, that is MIP, that is molecular imprinted polymer. So MIP is generally described as synthetic receptor for substitution of biological recognition element. So it is replacing the biological recognition element's job. That's the thing. So the technology happening here is an artificial lock with the ability to identify keys. So only that keys fit for that lock. Okay, that is happening here. So from the figure itself, we can get an idea of what is happening here. That template, there's a template. So only the particular polymer can only trapped in that template. So the sequence of events that is happening, first one is template monomer complex formed through covalent, non-covalent ligand exchange. The template trapped within the polymer matrix during polymerization. After the template removal of the polymer matrix, these binding cavities are reactivated with the target molecule. So in our case, our target molecule is that is creatine. So after the polymer matrix removal, the template is filled with the creatine, that is our target. The target molecules are captured by the cavity. So next is monomer template interaction. The monomer template interaction is done through covalent and non-covalent imprinting, which is done through van der Waals forces, hydrogen bond forces, etc. And next is the synthetic strategies for molecular imprinted. That is the 5 strategies, that is traditional bulk polymerization, precipitation polymerization, suspension polymerization, emulsion polymerization, surface polymerization. These all polymerizations are done. And next is the technique of MIP assembly on sensing device, that is on the transducing device. The MIP assembly, the first one is electrochemical polymerization, is directly in solution containing template and electroactive functional monomer. And the second one is drop casting of pre-prepared polymers from solution. And the third one is the synthesis of films by grafting polymerizable group. And the fourth one is layer by layer self-assembly of the transducer surface. And these are the 4 steps of MIP assembly on the sensing device or the transducing device. And this is a representation of the electropolymerization and drop casting method. So in drop casting method, we are putting a drop of the MIP coated on the transducing surface. And next is to determine the success of the imprinting process. For that, we are finding the equilibrium binding capacity distribution coefficient with that equation. The equilibrium binding capacity can be determined by Q is equal to Ci minus Cf by M into V. So here Ci is the initial concentration of the analyte, Cf is the equilibrium concentration of the analyte, M is the mass of the polymer, and V is the volume of the solution. So distribution coefficient can be determined by Ci by Cf by MCF into V. And next we are also finding the imprinting factor by QMIP and QNIP, and also can be determined through KDMIP and KDNIP. So how the QMIP and KD related things are discussed just earlier. So also the selectivity is defined by selectivity factor, selectivity coefficient, and relative selectivity coefficient. So here the selectivity factor can be determined by Q analyte and Q analog, and also determined by yeah, based on imprinting factor also. Next, selectivity coefficient and relative selectivity coefficient can be determined through these equations. And the relative selectivity indicate the magnitude of selectivity of the MIP in relation to NIP, where values greater than 1 imply that MIP is more selective to the analyte or the success of the imprinting. So next is the MIP-based electrochemical sensor. Here I'm explaining the voltammetric. In MIP-based sensor, the analyte capturing by MIP cavities alters the electrochemical activity, changing the redox current peak. But one of the main challenges is the poor electrical conductivity of traditional MIPs, limiting sensor sensitivity. So this can be overcome by incorporating conductive materials like metal nanoparticles, producing the MIP layer on conductive surface like graphene or carbon nanotube. And next is the potentiometric sensor. MIP coated potentiometric platform enhances the sensitivity by using a recognition layer on the potential transduction layer. From the figure itself, we can get a conclusion that first the graph showing that without and with using the MIPs. So with uses the MIPs, it's enhancing the performance. But it also have limited challenges include reduced sensitivity due to thick MIP layers and poor selectivity for small inorganic ions. These issues can be addressed by controlling the MIP layer thickness and developing ligands that selectively coordinate with target ions by improving the sensor performance. And next, finally, and the last objective that we have in our seminar, that is MIP for creatine detection. Finally, we are getting to the detection of the creatine. So here we are incorporating MIP layer detection of creatine. So we are using reduced graphene oxide and polydopamine PDA. So here the dopamine is polymerized to form polydopamine PDA, and graphene oxide is reduced to form reduced graphene oxide. Uh, so this is the overview of the surface and the representation of the MIP synthesis detection process based on POC sensing platform. So the electrochemical behavior of RGO modified electrode can be done through CV. The CV cyclovoltammetry is employed to investigate the electron transfer property of the our proposed detection of the creatine. So here from this graph itself, we get a conclusion or we get an idea of the peak is going downward and upward. So from the CV graph, we get a concentration or the concentration between of the concentration range of the creatine. So from the graph, we get a the concentration of the creatine in between minus 0.4 and 0.4. So from the CV graph, when we plotting CV, we get the creatine range or the detection range of the creatine can be infer or get from this CV plotting. After we are plotting the DPV response, that is from the results of the CV, we plotted the DPV, that is differential pulse voltammetry. So here we get the final peak at which the concentration of the creatine, corresponding concentration of the creatine we are getting from the CPV. So this figure, the right side figure represent the STEM images and STEM images. So the mesopores presence and absence also find that the molecular imprinting success and it enhancer sensor performance, etc. And efficient determination of the creatine also can be get from these images. And finally, the POC readout system. The POC readout system of the proposed creatine detection method. So here there might be modified electrode detecting the creatine and corresponding voltage is given to the microcontroller, and microcontroller finally uh, get into the conclusion what how many concentration of creatine detector or not. So this is a representation of the POC readout system. And finally into the inference that this table represents the summary of the analytical performance of creatine detection using the just set about the method RGO-PDA MIP electrochemical sensor for creatinine detection. So in that method, we are getting a concentration range of 100 to 10 raised to 12 and correlation coefficient is 0.996 and related standard deviation of greater than 8 to 8.2 percentage and the limit of detection, a very low limit of detection can be detected using that method and selectivity of maximum 9.6 percentage of target signal. So POC sensing platform demonstrated a record low limit of detection and wide detection range of creatinine, showcasing its capability to detect analytes for femtomolar levels with high precision. So the platform offers a cost-effective, user-friendly solution with fast sample to result time, making it very ideal for diagnosis and the early detection of the creatinine. And then to the comparison of the MIP-based electrochemical sensor and the conventional electrochemical biosensor. So from the table itself, we get a conclusion that the MIP-based electrochemical biosensor is offering high operational and storage stability and improved selectivity, ultra-sensitive detection with lower limit of detection, and typically non-enzymatic. So the enzyme storage stability related issues are not happening here. And simple fabrication with fewer steps involved, less or no pre-treatment required, allowing for more straightforward and rapid testing. Highly suitable for point of care application due to compact design, robustness, and ease of use. And in case of conventional electrochemical biosensor, it also have some of limitations such as limited stability, often prone to some of the interferences, sensitivity may be limited, enzyme dependence, so the storage stability of the enzyme is one of the major limitation that we are facing, and most complex fabrication compared to the fabrication of the MIP-based electrochemical biosensor, etc. So the use of antibodies in biosensor presents specific challenges, including orientation issues on the transducer, as well as limited device lifespan and storage stability. Molecularly imprinted polymers offer superior chemical and temperature stability, can be tailored to specific target molecules and enable cheaper production, making them a promising alternative to antibodies in biosensors. So finally, into conclusion and my future scope work of my seminar, that is MIP provides significant benefits for electrochemical biosensor, including tailored production methods for specified targets, excellent chemical and thermal stability, reduced reliance on animal testing, and low-cost production, making them highly suitable for various applications. So MIP is really helpful, and when it came into effect, the MIPs will be very helpful for detection of very biochemistry related lab analysis. So the major challenge is optimizing production method to achieve biologically relevant detection levels while enabling scalable mass production. Addressing issues with electropolymerization, bulk polymerization, other synthetic methods is crucial for advancing practical application. Given advantages of MIP, future research should focus on developing scalable, efficient production techniques and overcoming existing synthetic method limitation to enhance the practical deployment of MIP-based sensors in clinical and home monitoring applications. These are my references. That's all about my presentation. Thank you so much.